All right, now that you understand what elements are and you understand what the periodic table is, we are getting very close to the idea of being able to draw atoms. So remember that an atom is the smallest unit of matter. It's the smallest unit of matter that you can get. So we're very close to being able to draw an atom. Before we do that, I want to talk though about atomic theory. So it's a little bit of a history lesson, but it helps you to understand what we used to think atoms looked like before and what we think atoms look like now. So I'm going to do a small disclaimer. The model of the atom that we're going to end up with is actually not the most updated model of the atom. However, it's a model of the atom that we actually use in grade 9, grade 10, and grade 11. Why? Because it's very easy and it covers our needs in grade 9, 10, and 11. If you're still taking grade 12 chemistry with me, I'll update you on the newest model of the atom. I just don't want you to get to grade 12 and think I lied to you and said that the Bohr-Rutherford model is the best. So let's take a look at atomic theory. We are going to go back in time and we're going to look at our very first one, and this is Democritus. So Democritus was a Greek philosopher. He also studied chemistry, physics, was kind of a jack of all trades. He worked with this gentleman named Leucippus, and they came up with the idea that matter cannot be divided infinitely. So he said if you take something, let's say you take a piece of paper. So if you take a piece of paper and you rip it in half, and you rip it in half, and you rip it in half, you're eventually going to get to a piece of paper so small that you can't rip it in half again. So matter cannot be divided infinitely. Eventually, you'll get to the smallest unit of paper or whatever you're dividing, and that's what he called the atom. So he proposed the existence of an indestructible, indivisible particle called atoms. He actually called them atoms. We shortened it to atoms later. Next up, our next discovery was John Dalton. So John Dalton wasn't just a chemist again. He was a chemist, physicist. He was also a meteorologist, so he studied the weather. He proposed the first modern atomic theory, and this was in 1803. So this Democritus and Leucippus had a model of the atom. It's not modern, though, because they didn't actually have any scientific evidence to back it up. John Dalton had his 1803 model, and he called his the billiard ball model. So the billiard ball model, I don't know if you know what billiards is, but billiards is like pool. So think of like a pool ball. When you describe a pool ball to me, it's a solid ball that actually is one thing that can't get any smaller, right? So it's a solid sphere. That's what he pictured an atom to look like, was a solid sphere. He also had 5 different points of atomic theory. So he had 5 different things that he said these spheres were like, or 5 different rules that these spheres have to follow. He said that all matter is made up of tiny, indivisible particles called atoms. So that was very similar to what Democritus said. He said that atoms cannot be created or destroyed. So you can't make atoms. All the atoms that exist in the world are all that will exist. And you also can't destroy atoms either. He said that atoms of a particular element are identical. So let's pick a random element, carbon. He said that every single carbon atom will all look the exact same. He said that compounds are formed through the combination of different elements. So a compound we know is one or more atoms. So a compound you might have, let's say this is carbon. And then let's say that this is oxygen. So he said that a compound is actually going to form when you have 2 different atoms and you combine them together. Chemical reactions are going to involve the recombinations to form new substances. So again, let's go back to our example where we have our carbon and we have our oxygen. And let's introduce a third party. Let's introduce a sulfur. So he said that a chemical reaction is going to form when you take these elements and you actually recombine them. So maybe we're going to have oxygen is going to stay the same, but maybe sulfur is going to come in and form a bond. And carbon's going to be left out on its own. So he said that We have these small indivisible particles. They look almost like billiard balls, and we can actually go through and arrange them. And by arranging them in different combinations, that's what a chemical reaction actually is. So his 5 points actually held up pretty well, and his 5 points actually helped to explain a lot of different parts of chemistry today, but there was a few problems with it. So we had J.J. Thomson come around next. J.J. Thomson, what he did is he studied the tiniest atom that came from the inside of a metal electrode. He thought he was studying an atom. He actually wasn't. So what he essentially did is he was studying an electrode, and he noticed this tiny little small thing in the electrode that was actually smaller than an atom. So he called this a subatomic particle. Subatomic meaning smaller than an atom. So he noticed that there actually is something smaller than an atom, and he called these particles electrons. So he said these electrons must exist, and this led to his idea of the plum pudding model. So plum pudding, again, it's an old British dessert. You might not know what it is. So I oftentimes call it the blueberry muffin model. So we're going to picture a blueberry muffin, so a nice big cakey muffin with a bunch of blueberries strung throughout. So the blueberry muffin model essentially said that we still have that sphere shape that we saw before, but with the sphere shape, we now have these little dots, these little blueberries within, and these little blueberries are called electrons. What electrons are negatively charged subatomic particles. So electrons are these negative charged particles. We're going to talk about these more in our next lesson when we talk about Bohr-Rutherford diagrams. So we have our negatively charged particles, and then we have this positive space. So if you want to think about your blueberry muffin, the cake part of your muffin would be this positive space, this positive sphere. And the blueberries would be these negative little dots. So we don't just have a solid sphere anymore. We still have a sphere, but a sphere within these dots. That was the plum pudding model. Next up, we had this gentleman named Rutherford. Now, I absolutely love Rutherford's experiment, so I talk about it all the way up to grade 12. So what Rutherford did is he proposed that a beam of alpha particles have enough energy to shoot through a piece of thin gold foil. So let's slow down and let's talk about what alpha particles were. At his time, alpha particles picture almost like a laser beam. Not quite a laser beam, but for his time, very high charge energy. So he's got these alpha particles, and he's going to shoot these high-powered alpha particles at this little tiny thin piece of gold foil. So what he expected to happen, as I'm sure you expect to happen, he expected the alpha particles to blow right through this piece of gold foil, pass right to the other side. Now, the interesting part of his experiment is this actually initially seemed to work. It actually worked 9,999 times out of 10,000. So it worked most of the time. But sometimes it didn't work. So I'm just going to zoom out so you can see this whole picture. So sometimes the particles didn't shoot right through. So he's got this alpha particle, he's shooting it at this gold foil. Most of the time it passed right through, but sometimes it bounced right back, or it was deflected. So deflected means that it just kind of passed off, it changed course. So it didn't go right through, it either changed course or it bounced right back. So what this suggested to Rutherford is this high-powered beam must be stopped by something. There must be something solid in that middle that's actually able to stop this high-powered beam from passing all the way through. However, it doesn't stop it very often. Most of the times it passes right through, only sometimes it bounces right back. So since it's not stopping it very often, whatever's stopping it must be incredibly small because the beam's not hitting it very often. So again, what he expected to see was it to pass right through. Instead, he saw most of the time it passed right through. Sometimes it deflected or reflected, so bounced back. So what he came up with is he said there must be some sort of positive charge that's very dense at the core. So he called it small but massive. So he said in the very center of the atom, there must be a little tiny positive core that's very dense, and any time that the alpha beam hit that positive core, it bounced right back. So he said that yes, the atom is mostly still empty space. Most of the time it's empty space floating around, but it's got a positive core in the middle. He called this the planetary model. So he called this a planetary model because you have a positive core with a bunch of stuff orbiting on the outside. He said it must look like our solar system. So the planetary model, picture the very dense positive core to be the sun and everything else floating around it to be the other planets. Our last model is called Bohr's shell model. It's pretty complicated for the physics. So again, I'll explain this more in grade 12 with the physics. Right now, we're just gonna look at the 3 different rules. So Bohr's shell model actually looked at electrons. So he said that electrons actually aren't just floating all kind of willy-nilly like they are in Rutherford's model, but instead electrons have to be in certain spots. So electrons can only occupy certain discrete orbits or energy levels. So let's actually draw this. Let's actually draw what this model might look like. So based on what we know about Rutherford, we've got this positive core. And based on what we know about Bohr, we've got electrons floating around the outside, but the electrons are in certain energy levels. So what that means is they can only exist in certain spaces. They can exist maybe in this space, or they can exist in this space, but they can't exist in between. Picture it almost like rungs of a ladder. When you're climbing a ladder, your foot can sit on the first rung, it can sit on the second rung, but it can't hover between the 2 rungs because there's nothing there to support it. So he said that electrons actually have to sit in these certain energy levels. They can exist there without losing energy. They can also change levels by absorbing energy. So they're able to change levels by either going up or by going down, by absorbing or by releasing energy. Let's get rid of this. So a little bit more about Bohr's model. He got actually a little bit more specific. He said that the orbits can hold a certain number of electrons. So he actually defined how many electrons can be in each orbit. He said there could be 2 in the first, there could be 8 in the second, there could be 8 in the third, and then afterwards his theory doesn't really hold up. So again, I said that this is a great model. We're going to use this model for grade 9, grade 10, and grade 11. And then in grade 12, I'll introduce a new model that'll hold up that we can get past calcium. Bohr also said that when an inner orbit is filled, electrons occupy orbits further from the nucleus. So again, let's draw what this is going to look like. We've got our nucleus, we've got our positive core. And next up, we're going to have our first orbit. So in this first orbit, we can have 2 electrons can fit there. What happens if you have more than 2 electrons? Well, it's full. So all of a sudden, we must have a second shell. Our second shell can now fit 8 electrons. What happens if we have more than 8 electrons? Well, they didn't hire me to draw circles. My circle drawing's terrible. We go to our third shell. So the idea is that once an inner orbit is full, I go to the next orbit, to the next orbit, to the next orbit. Neat thing about Bohr's shell model, it finally explained why the periodic table was arranged the way that it was. So Bohr's shell model came out in the 1900s, and Bohr's shell model actually perfectly lines up with those trends of the periodic table. I'll talk about that a little bit more in our next lesson. So your head is probably spinning right now because you're still wondering, after all this history lesson, I have no idea how to draw an atom. So what we wanted to do is we just wanted to go through and talk about the different discoveries that led to the different parts of the atom. So we used to think the atom was a solid sphere. Then we said, not really, it's a solid sphere with a bunch of blueberries or electrons throughout it. Then we said, it's actually probably with a core with electrons floating outside of it. And then Bohr came along and said that the electrons are floating outside, but in really specific spots. So our next lesson is going to be called Bohr-Rutherford diagrams, and we're going to learn exactly how to draw the atom based off of our rules then. What I recommend is there's a video, so it actually walks you through what some of these might look like. And then I also actually put a chart in there as well too. So I put a chance for you to organize a chart. The chart is blank. It's blank on purpose because I want you to actually go through and organize your thoughts. This is a tough concept, so I want you to think about it. I want you to go through and I want you to summarize what each of these models actually looks like. And then I'll post my answers to the chart so you can actually go through and compare. One last thing that I wanted to mention, we're not going to mention right now, or we're not going to learn about it right now, but I do want to mention this idea of the quantum theory. Quantum theory is that model we're going to learn in grade 12. So I want you to kind of just remember the name. If you hear someone talking about quantum theory, it's the most modern model of the atom. It's also called the electron cloud model, and it's the reason you should take grade 12 chemistry, because I'm going to have a chance to actually show it to you then. Last person we want to mention, because he's in your chart, he actually doesn't have a model of the atom, but he had a very important contribution to the atom. In 1932, Bohr was making his discovery. Rutherford was making his discovery. So Rutherford talked about the positive core, the protons. Bohr talked about the electrons. And Chadwick said, I think there's actually another particle. This particle must be the neutron. So Chadwick did discover the neutron. He didn't necessarily have a model of the atom, and the neutron is going to play a very important role in that Bohr-Rutherford diagram we're going to talk about next lesson. So join us next lesson. We're going to take protons, we're going to take neutrons, we're going to take electrons, and we're going to show you how to draw an atom. Have a good day. We'll see you soon. Bye.